Hey, welcome back. So in this video, we're going to see one way of remembering or storing the answers to the repeated subproblems. So we solve fib of 5 once and we remember it, so next time we don't have to do any of this. And that's going to speed things up a lot. So the strategy I'm going to show you now is called memoization. And the idea is that we have some structure to store data in, an array or an object usually. And then we do whatever expensive function call, let's say fib of 5, and then we store it in that array so we can come back. And next time, if there's another fib of 5 call, instead of doing all of the work, we simply look in our table or our array, whatever it is, to see if there's a fib of 5 in there already. And if there is, we just use that piece. So we remember we've already solved it and we cached it and we don't have to do it again. So if you want to try implementing a version of this, you can take our exact same recursive code that we've been working with for Fibonacci, but just change it a bit, use an array or an object, and see if you can work out a way to make that work. I'm going to show you a solution right now. It's not necessarily the shortest possible solution. I wanted to make it nice and easier, well, as easy as possible to understand. So let's talk about how it works. So we have our fib function. It takes an n. Let's say we're looking for the 5th number. There's also the second thing, memo, and this is where we'll store the answers we've already found to those subproblems. So we solve them once, we add the answer in here, and then if we need to get that data or that answer again, we look here instead of recalculating it. Let's say that we find fib of 3. We're going to store the answer at the 3rd index in our memo. If we find the 10th number, let's say we're trying to calculate the 20th Fibonacci number. Well, if we already found the 10th somewhere down that recursive tree, we store it in here under the 10th index so that we can then find it easier. Okay, so basically we still have the same base case. We have the same recursive call, but things are slightly different because the first thing we're going to do is check. If we're looking for Fibonacci of 5, have we already solved that? Do we have something at the 5th index in our memo? If we do, we just return that value. So that short circuits everything. So after the first time we find fib of 4 or 3 or whatever it is, it's going to be stored in memo, and we can short circuit it by pulling it out. We also have our base case. So if we're looking for first or second digit, we return 1. But any other time, here's our recursive call. We pass through memo, which will, accumulate our data. And we don't have to do it as a separate variable like this. I just broke it up to make it clearer. So we calculate this number, and then we store it under n in our memo, and then we return it as well. So here's a simple animation that sort of walks through what I'm talking about for fib of 5. So here's memo. Technically at the start, it wouldn't look like this where we have these empty slots. It's just going to be totally empty. There's nothing in it anywhere. There isn't a 2nd or 3rd index yet, but just imagine this is all empty. Notice I put an X through 0. We're not calculating the 0th Fibonacci number, so I'm just leaving that alone. It will always be undefined. You could alter our logic so that we're always doing, storing things 1 over, shifting it by 1. That would be fine too, but this works. So when we calculate fib of 5, it calls fib of 4 plus fib of 3 because we don't know what fib of 5 is. Well, we don't know what fib of 4 is. Same thing, this is not new. Cascades down until we hit a number we know. Fib of 2. Well, that's going to return 1. So then what we do is go over to our memo and say, okay, I know what that is. Fib of 2 is 1. So we put it under the 2nd index. And we're done there. Now we add it together to fib of 1. Well, what is that? We also know that because it's our base case. So we store it inside of our memo at index of 1. Now fib of 3 has those two values, 1 and 1, adds it together and we get 2. And then we're going to say, all right, fib of 3 is 2. Let's store it there. So if we need it again, which, hint, hint, we need it over here, we can find it. It's 2. So now back to fib of 4, it's adding together 2 plus fib of 2, which is 1, gives us 3, and then we store it in our memo. Even though we're actually never going to use that because we don't need fib of 4 again. We only need it once right here. But anyway, we store it in there. Then we go to the right side. And this is where the magic happens because we don't need to do any of this. Whatever was over here, let's say we're on a much larger scale, which would be really difficult. This diagram took way too long to get all these animations. It's kind of a pain with the slides I use. But imagine how fast that tree grows. We saw that a couple videos ago. It scales really quickly. Anyway, the logic this time says, okay, fib of 3. Wait, do we know fib of 3 yet? Before we go calculate it all, do we know it? Yeah, we do. We already did it over here. So we just take 2 as our answer, and we skip this. So in this case, we're only skipping fib of 2 and fib of 1, but if we're doing fib of 7, let's say, it would be a huge difference. I'll go back to that slide that shows it in a moment. So we short circuit that, and then we get our answer, which is 5, by adding 3 and 2. And then we potentially store it. That part doesn't really matter if we're adding it in or not. But anyway, the point is we remember what we've done so that we can save some work. So to go back to this fib of 7 example, imagine this. The first time we calculate fib of 5, we can store whatever that answer was, which is 5, I believe. And then all of that is saved over here. We don't have to do any of this work anymore because it's stored in our memo. Same thing, fib of 4 is stored in there. And so once we get to fib of 4 here, we can use that. And we wouldn't even need to use it here because we would have stored fib of 5, which removes this entire chunk anyway. So now imagine fib of 100. It's going to be a huge tree with a lot of those limbs chopped off, saving a lot of time. Now to show you just how much better it is, I'm going to run this. And we can start with the basics. Fib of 5, we get 5, cool. Fib of 10, we get 55. Now remember that as I started to do things like fib of 30, it took longer. Fib of 40 took like multiple, I want to say almost like 10 seconds. Fib of 100 broke my browser last time. And check it out how fast it's happening. It's actually being calculated before I even hit enter. Now, the biggest problem we run up against is that Fibonacci numbers grow so quickly that numbers like integers in JavaScript can actually hold them, and then we start to lose accuracy. But it's working. It's way, way faster, a huge improvement. In the next video, we'll talk about actually the big O notation of it. But in this video, I just wanted to introduce the idea of storing our data in a memo. This is not the only way of doing that. We could have used an object. We could have had an object that looks like this, where we stored, 2. The first Fibonacci number is 1. The second one is 1. The third is 2. We could have done that with appropriate commas. Another thing that we could have done, you may have noticed this if anyone tried to run this or print it out. Like if we print out what our memo looks like, I think Chrome will only show me the last version of it. But if I do fib of 6, you'll see that we don't actually store anything for 0, of course, because we didn't use that. But 1 and 2 aren't stored in there because we just return the value. So that's fine. It's the base case. But what we could also do to potentially shorten things up is this. I could just put everything in here so that the default is undefined 1 and 1. We sort of pre-program in the basics, and then I can actually get rid of the base case entirely. And now, when I run this code, we already have 1 and 1 in there. So we don't need a base case, because if we're looking for the first or the second digit, this line will return 1. So it's just a small change. If anyone was wondering, some people would think this is a little clunky. And the other thing that I didn't point out, if you were doing this frequently for some reason, calculating these numbers, you would want to make this probably a separate variable, store it somewhere else so that you didn't recalculate it every time you ran this. You would just store those numbers. But that's not really the focus here. So that's it for memos for now. In the next video, I'm going to show you how we figure out the big O and how much better it actually is. It's a huge improvement, as you could already tell. But to summarize, the idea behind memoization is using some structure where we can log whatever result we found for a subproblem so that next time we don't have to repeat all of that work. We just look it up in our data structure, in our case, an array.